Class 9, Lagrange Multiplier. In mathematical optimization, the method of Lagrange Multiplier, named after Joseph Louis Lagrange, is a strategy for finding the local maxima and minima of a function subject to equality constraint. So we can use this Lagrange multiplier method when we want to optimize a function subject to some constraint. For the case of only one constraint and only two choice variables, x exemplified in figure 1, consider the optimization problem, maximize fxy and subject to gxy and z. Let's take a look at figure 1. What is this? So this is figure 1, Wikipedia. Okay, so f looks like this and g. So we want to measure fx, and clearly global maximum is over here, right? So this is mountain. So it's mountain at its peak, and but there is a constraint. We want the highest point of the f, this mountain, but only subject to this red line. So this is the road or trail we can take. So basically, under this constraint, we want to find the highest point, which is somewhere over here, that is, and this tangent, right? So in this trail, we want to find the highest value of this trail, which is again somewhere over here. Okay? We assume that both f and g here maximize f subject to g equals c. We assume that both f and g have continuous partial derivatives. And we introduce a new variable lambda. This is the point. This is important point. When you optimize it, we introduce new variable lambda called Lagrange multiplier, and study the Lagrange function or Lagrangian expression defined by this one. So instead of analyzing this problem directly, from now on we analyze this one, this Lagrange function. This Lagrange function here, f is this objective function, and g minus c is this subject part, and lambda, this is the Lagrange multiplier, very important one, where lambda term may be either added or subtracted. If fx naught y naught is the maximum of fxy for the original constraint problem, then there exists lambda 0 such that x0, lambda 0, y0 is the stationary point of Lagrange function. So here, instead of finding stationary point or critical point of this one, because we have subjected, now we want to find the critical point of this one, and we regard lambda as one of the variables that we want to minimize. Okay, so we are now, instead of finding critical point of this one, we want to find critical point of this Lagrange function. x0, y0, lambda 0 is stationary point for the Lagrange function. Stationary points are those points where the partial derivative of lambda, Lagrangian, are 0. Basically, first order condition or gradient of lambda are 0. However, not all stationary points yield the solution to the original problem. Thus, the method of Lagrange multiplier yields the necessary condition for optimality, because there is possibly saddle point, right? Maybe we want to find the maximum point, but it may lead to minimum point or something like that. It has general problem of the first derivative approach, gradient approach. Sufficient condition for minimal maximum also exist. For the general case, now we have general case. For the general case, of an arbitrary number of n of the choice variable. Now we have number of more choice variable, and then we have n. So it is multivariate function. F is multivariate function, and we have more than one constraint. Now the number of constraint is m. An arbitrary number m of the constraint, the Lagrangian text form of now we have new number of arguments from x1 to xn and lambda 1 to lambda m and f and like this one, where the constant term of each constraint have been subsumed in the function gk, so that case constraint like this one. Right? Here we can move c over here, then we can make this one 0. So this is for convenience, no combination notation. So we are moving this one over here. Again, the constraint optimization of f coincides with the stationary point of lambda, or stationary point of this Lagrange function. So, for this constraint optimization problem, what we do is basically we define new function and we find the critical point of this one, critical point of x and lambdas. That's our strategy. Now the interpretation of Lagrange multiplier, or let's take a look at this one. Here, we can visualize contour of f given by f x y equal d for various value of d. And the contour of z is given by g x y equal 0. Now, how we can find this point? Clearly, this is the maximum point. So again, our goal is to find highest point of this one, but we can walk through only this one. So this is mountain trail, and in this mountain trail, basically we want to find highest point. Suppose we walk along the contour line with z equals 0, we may put c over 0, then it is 0. So it is without loss of generality. So let's see c is 0 without loss of generality. We are interested in finding the point where f does not change as we walk here. So if you are top around at this point, f is basically flat, not decreasing, not increasing. So around this point it is close to flat. It should be right. So we are interested in finding the point where f does not change as we walk. Since this point might be maxima, there are two ways this could happen. First, we could be following a contour line of f. So we are basically contour line of f. Then it is the same height. It's contour line, 등고선 in Korean, 등고선 contour line. So basically, we are following this contour and we are always at the same height, right? So if we could follow a contour line of f, since by definition f does not change as we walk along its contour line. So basically what our strategy is, when we walk through contour line here, then at some point we meet this trail, right? And then that's the highest point. This would mean that the contour lines of FG are parallel here. So at this point, they are parallel, right? They tangent each other. The second possibility is that we have reached the level part of the F. Level part of the F meaning that F does not change in any direction, like this one. Okay? So to check the first possibility, notice that since the gradient of the function is perpendicular to the contour line, so geometric interpretation gradient is this line, okay, or this line. Perpendicular tangent line, this tangent line, and the perpendicular line is basically intuition of gradient. So to check the first possibility, note that since the gradient of a function is perpendicular to the contour line of f and g should be parallel. Okay, since they tangent their gradient, this dot line, this gradient, that should be in the same direction. They are opposite, but anyway, they are the same line. They should be same direction, right? There should be same direction. So gradient should be same direction. So when they tangent each other, it means that their gradient is same direction because gradient is orthogonal, perpendicular to this tangent line. This tangent line. Therefore, by definition, so by that reasoning, the gradient of this level curve and gradient of this trail should be in the same direction. Like this, they're in the same direction, like. Although it is opposite, same direction means they're in the same line. Okay. So the contour lines of FLG, F and G are parallel if and only if the gradient of F and G are parallel. They are same direction, the same line. Thus, we want to find point x, y where gxy equals g is constraint and gradient of f and gradient is same direction, lambda. Okay. So here in this case, lambda would be negative, right? For some lambda, where this one is gradient of f, del f gradient of f, and del z gradient of z, where del f, del g are the respective gradients. The constant lambda over here, lambda is required because although the two gradient vectors are parallel, the magnitude of the gradient vectors are generally not equal. This constant is called Lagrange multiplier. In some convention, lambda is preceded by a minus sign. Notice that this method also solves the second possibility. If f is a level, then its gradient is 0, and the setting lambda is 0 is a solution regardless of z. Okay, so this happens when f attains at global. By chance, this one will pass through the highest point. To incorporate this condition, so we want to derive this one. To incorporate these conditions into one equation, we introduce an auxiliary function, i.e. Lagrangian, like this one. Lambda, Lagrangian x, y, lambda is fxy minus lambda zxy. Here we set constant 0 because we move c in the previous equation. And we want to calculate the first order condition or gradient equals 0. So we calculate del lambda equals 0. You want to do this one. Notice that this amounts to solving three equations in three unknowns. This is the method of Lagrange multiplier. Note that del lambda part Lagrangian is 0 implies that G equals 0. Because we take derivative of this one with respect to lambda, then we have only this one, right? And to make 0 means it is constraint. So to summarize, del Lagrangian is 0 is same to del f equal to lambda del plus this constraint, right? So basically now instead of just looking for this one, we have more compact, convenient notation. So we can just investigate this one. So the method generalizes readily to functions of n variables. Now we have n variables like this one, which amounts to solving n plus 1 equation in n plus n unknown, because we in this gradient we have argument of n and last one is lambda, right? So we have n plus 1 element in the gradient and it is 0, so we have n plus 1 equation and n plus 1 unknown, so we can solve it. Now how about we have multiple constraint? This is the one. So basically still, as I explained, we have Lagrangian, then we set up Lagrangian like this. Now this lambda looks like this. We have multiple lambda. So solve del Lagrangian, which is equivalent to, we have this one, same gradient with the same in the parallel line, and then parallel to each other, and then we have constraint. We have m constraint, which amounts to solving n plus m equations in n plus m unknowns. Now, we please work on the examples presented at the link above. So let's take a look at the first example. Yeah, let's take a look at this one. Example 1. Now, suppose we wish to maximize fxy equals x plus y, subject to the constraint x squared y squared 1, right? So, well, so feasible set. So the problem like this. So x plus y is like a plane. The three-dimensional plane. Okay. So, well, this is as x increases, y increases, this increases. So basically, the maximum is undefined. But now we have this constraint of a circle, right? So basically, we want to find this point. Likewise, because this is slope in this direction, minimum would happen somewhere over here, right? So the feasible set is the circle, and the level set of f are diagonal line, slope minus this one. So we can see graphically that maximum occurs at this one and the minimum occurs at this one. Let's take a look at this. So here, so this is x and y. So constraint is x squared y squared equals 1. So the constraint looks like this one. So again, like this, and then, well, let's make it this one blue, okay, blue, and then we have right, this is x, and this is y, and this is basically 1, right? And this is the minus 1, and this is basically x squared plus y squared equals 1, right? And then we want to find the maximum of x plus y subject to this circle. So x plus y would be look like this. Well, it is not exactly x plus 45 somewhere, right? So basically, yeah, so we want to find the maximum of this one, but we can find this one. So clearly, maximum would happen somewhere here, and the minimum would happen. So and then minimum would happen somewhere over here, right? So minimum would happen somewhere over here. So minimum would happen somewhere over here, right? And then this is the, let's say, sky blue. So if you calculate this one, clearly this would be, the maximum would be somewhere over here, right? So this point is the, because it's 45-degree line, so it is 1. So x, y is the cosine. This is basically 4 over pi, 45-degree line, 45-degree, right? And then 45-degree. So we know that max over here, mean over here. So it is 45. So cosine of 1 is x-axis, and sine of the 1. So this is max is the basically cosine pi over 4, which is 45, sine pi over 4, right? Cosine sine which is basically over 2 and then 2, right? And likewise, this minimum point, we know this minimum point is the 1, so it is the 45, so it is a pi plus 45, so basically cosine of sine of 4, and then this we know this one is minus over 2. This is minimum maximum. We know this one. And then let's take a look at whether, so basically we are looking for mean. The problem of this one is basically what we do is basically mean of x plus y subject to x squared y squared is 1. Then solution is this one. And then if we do the max x plus y subject to x plus y squared is 1, then the solution is basically this one. Right? We know this one. And let's check whether our Lagrange approach finds the solution correctly. Okay, so using the method of Lagrangian, we define z is this one. So subject condition is this equal to 0. So the Lagrangian, we have x, y, and it is constraint or one constraint. So we have one Lagrangian. So one Lagrangian multiplier lambda. So Lagrangian of x, y, lambda is fx plus y plus lambda gxy. And x plus fxy is x plus y over here, same to this one. So x plus y and plus lambda, and then we have x 제곱 plus y x squared plus y squared minus 1 over here. Now we calculate gradient, so del of Lagrangian with respect to x, y, lambda, then it is partial Lagrangian over partial x, partial Lagrangian over partial y, and partial Lagrangian over partial lambda. Then x is this one 1 plus 2x lambda. And then if we take derivative of y, then we have 1, and then y squared, so 2y lambda, 2 lambda y. And then if we take derivative with lambda, then we have this one, so x squared plus y squared. So this is the gradient. So we want to find this one equals 0. This one equals 0, and this is this one. And then if we take a look at the first two equations, you can basically see x and y are same, right? X, y are same, because if we solve the first two, then x and y is same to minus 1 over 2 lambda. If we put minus 1 over 2 lambda over here, they are clearly 0. So lambda shouldn't be 0, clearly. And we substitute x, y, minus 1 over 2 lambda into the constraint by substituting this into the last equation, which is constraint. So 1 over 4 lambda squared, and this one is 0. So if we solve this one, lambda is plus minus 1 over root 2. So if we plug this one over here, then we will get the solution. Right? This which implies that the stationary point of the Lagrangian are either this one, so we have two solutions, this one and this one. Here the last one, because is the value of Lagrangian, right? So clearly this point corresponds to this one, and this point corresponds to this one, right? This one. Evaluating the objective function f at this point, f, this one is root 2, and if we put this one into objective function x plus y, then it's minus root 2. Thus, the constraint maximum is root 2, and the constraint minimum is minus root 2. And so here, Lagrangian, let's find the red. So Lagrangian, we said Lagrangian is x plus y, and then we set up, if we use notation same to Wikipedia, it is plus lambda x squared plus y squared minus 1. Okay, which leads to either min max. Okay, so yeah, actually I want to highlight this one. This is maximum and this is min. Right? Lagrange. Now we have a second example. Now we modify the objective function of example 1 so that we minimize x plus y square. Now instead of x plus y again along the circle this one. Now the levels of the f are still lines of slope minus 1 and the point on the circle tangent to these levels is again this one, this tangent point is this one. On the other hand, the minimum occurs on the levels of the f equals 0. Since by its construction, f cannot take negative values because it's square at this one and this one, where the level curve f are not changed to the constant. The condition that delta is correctly identify all 4 points x equal to the minimum are clearly characterized as particular lambda equals 0. Okay, so you can solve it. This one. Now another example. In this example, we will deal with some most tenuous calculation, but it is still a single constraint problem. Now suppose we want to find the maximum value of fxy equals to x squared y with the condition that x and y coordinates lie on the circle around the origin with radius √3. That is subject to, our subject to is x squared plus y squared minus 3 equals 1. As just there is just a single constant, we will use only one multiplier, say lambda. Now the constraint gxy is identically 0 on the circle of radius 3, √3. See the any multiple of gxy may be added to fxy, leaving the fxy unchanged. So even if we multiply this one as any number, is the same in the region of interest. So basically, this one, this x squared right, is this the complicated mountain, and we want to find the critical point of this mountain, strange mountain, subject to this trail, and in the mountain, this trail corresponds to this one. So now we apply ordinary, the Lagrange multiplier method. Then again, Lagrangian xy lambda is fxy plus lambda gxy, which is x squared y plus lambda x squared plus y squared minus 3. Now again, we can calculate the gradient such that del lambda xy lambda del L Lagrangian xy lambda is again this one, and if we take the partial derivatives of this one, take derivative x, then 2xy and 2x lambda, right? If we take the lambda, then it's y, then it's x squared, so x squared plus again 2 lambda y. If we take derivative of lambda, partial derivative lambda, then we have only this, we have constraint of this one, and therefore this gradient of Lagrange equals 0 means that we have this one and this one. If we divide this one and manipulate this one, is basically same to this one. So we have 3 equations, 3 unknown, we can solve it. Now, so we can find the solution. So we can find the critical point. We have 6 critical points over here. We have 6 critical points. Right? So if we solve 6 critical points and evaluating the objective at this point, we find that for this point 2, for this point minus 2, at point 0. So therefore, the objective function attains the global maximum subject to the constraint at this point. So this point corresponds to either this point or this point. So this highest point. Oh, sorry, this point or this point. They are highest point in the train. And then what? global maximum and minimum, global maximum, or at the constraint this one, and the global minimum at the point plus minus root 2 minus 1, and then the global minimum is this point, right? This minimum track. Now, how about those things? At this point, it is 0, f is 0. Therefore, this for the local minimum of f and this local maximum of x as may be determined by consideration of Hessian method. We don't know this one. So whether it is local minimum or local maximum, well, it is somewhere, I don't know, somewhere over here. So it is around this area, maybe this one. I guess one is this one and the other one is this one. Another one is likely to be local. It is lower than this one, and this is the higher than this one. So they are not either global maximum or global minimum, but they are in the local area. They are critical point. They are local maximum, local minimum. Now, we have another interesting point. Note that while this one is a critical point of Lagrangian, it is not local extreme. We have this one, so given any neighborhood, this one, we can choose a small positive epsilon and small delta of either sign to get Lagrange value both greater and less than 2. So this can also be from the fact that Hessian metric evaluate the point is indefinite matrix. So at this point, root 2, 1, at this point, which is this point is a saddle point. It is either maximum or minimum. So this one solve again, this point, this one solves this one, but it's either maximum or minimum. They are saddle point. And then the saddle point, look at this somewhere over here, I guess. Somewhere over here, saddle point, I think. So in this way, it is increasing, yes. I don't know, but yeah, it is saddle point about, should be around here. Now another entropy. Entropy is another interesting example. Entropy. Suppose we wish to find the discrete probability distribution on the point P1 to Pn with maximal information entropy. What we mean by maximal information entropy, you can check it. This is the same as, so maximal entropy, information entropy. You can check this link and you have a better explanation, but let's skip. But briefly speaking, this maximal information entropy, this is the same as saying that we wish to find the least structured probability distribution on the point of this one. In other words, we wish to maximize the Shannon entropy equation. Well, you don't have to know. But anyway, our goal is to find the set of P. They are all probabilities such that we want to maximize this one. So maximizing this one is identical to minimizing this part, right? So we want to maximize the minus of this one. So with this to be the therefore, but this P1 to Pn, they are the probability, so they should be summed to 1 because they are probability distribution, discrete probability distribution. If they are continuous, they should be integrated to 1, but they are discrete probability distribution, they should be summed to 1. For this to be a probability distribution, the sum of the probability pi at each point xi must equal to 1. So our constraint is this one. So you don't have to know entropy, but anyway, our goal is to maximize this one, and constraint is this one. Again, we set up Lagrangian. And we find the first order quantity or gradient set equal to 0. So this is Lagrangian. This is Lagrangian. F plus lambda g minus 1 because it's 1. So this is Lagrangian, and we take derivative with respect to p, actually plus lambda, and we want to set it 0, which gives the system of n equation looks like this one. And then carrying out the differentiation of this n equation, we get this one. This shows that all p stars are same, right? So if we take differentiate this one, which is this one, because they have all same, differentiation. So it means that pi, so intuitively you can guess from this one. We guess this p are all same, right? P are all same. Well, they should be summed to 1, and because this p are all same, they should be 1 over n. Hence the uniform distribution, this is uniform distribution, is the distribution with the greatest entropy among distribution over n points. This is enough. And then let's take a look at second example in Khan Academy. Let's click this one. Yes, quick step. We have another very good explanation over here. Okay, again, well, here this is looks even better, right? We want to find the maximum of the highest point of this mountain, but we can follow only this track. The point is here when the two lines tangent to each other, which means that their gradient should be perpendicular to each other in the same line. Okay. So when we want to maximize a multivariate function subject to constraint that another multivariable function equals constant to this one, basically we can follow this step. So this is beautifully viewed. Step 1, introduce a new variable lambda and define a new function Lagrangian as follows. Lagrangian x1 lambda equals f minus now Lagrangian g minus c. This function this L lambda is called the Lagrangian, and the new variable lambda is referred to as Lagrange multiplier. Step 2, set the gradient of L equal to the 0 vector so that del of this one equals 0 vector. So this is second step, first order condition. In other words, we want to find the critical points of this Lagrangian and consider each solution, which will look something like this, and we plug each one into f, or rather first remove the lambda 0 component, then plug it into the f, since f does not have lambda as an input. However, one gives the greatest value is the maximum point. Whichever one gives the greatest value is the maximum point you are seeking. So once you solve this one, then you have a bunch of solutions. Then you plug this solution into original objective function, and you can tell whether we have a maximum, minimum, or saddle point. Now this is an economics example. Suppose you are running a factory producing some sort of widget that requires steel as a raw material. Your costs are predominantly human labor. So cost of labor is $20 per hour for your workers, and the steel is $170 per ton. Suppose your revenue is loosely modeled by the following equation. So your revenue, so you put labor and you put steel, then it generates some revenue. H represents the hour of labor, and S represents tons of steel. Now, if your budget is $20,000, which is the maximum possible revenue. So, well, if you put more labor, more steel, you can get higher and higher revenue. However, there are your budget. You can spend the money you have of $20,000. So your goal, you have to align. You have to allocate $20,000 into either H and S, and then you want to maximize R. Now the solution, the $20 per hour labor cost and 170 per ton steel cost tell us that the total cost. Now the total cost of production is 20H and 170S, because there's cost of labor, cost of steel, combining them, you have total cost. And therefore the budget is 20,000, so our budget is like this one. So therefore the budget of $20,000 can be translated to constraint this one. So before we dive into a computation, you can get a feel for this problem using the following interactive diagram. You can see which value of HS is the given revenue, blue curve, and which value satisfies the constraint. So this blue curve is the 200h square and this one. Now this is your budget constraint. So this is your budget constraint, right? So you can spend money only this one, and by the set of possible way of allocating into labor still is at this line. So at this line you want to maximize this one. So what we can do is how we can do that, right? So yeah, so like this one. So revenue, well, the revenue, as we increase revenue, we have something like this. So basically we want to find this one over here, so we want to maximize this one. So yeah, when it was, so this blue line is ISO revenue curve, so it is a contour map of labor, so there is higher of this one. So as we move R, something like this one. So in the budget constraint, the maximum would happen somewhere here. So the answer would be somewhere at this point, right? So as you know, at this point they tangent to each other. So the maximum value would be somewhere over here, right? Since you need to maximize the function R, blue one, subject to the constraint, this one, so you want to find, we begin by writing the Lagrangian function for this setup. So Lagrangian Hs lambda is this one minus this one. Next, we set the gradient del Lagrangian equal to 0 vector. This is the same as setting each partial derivative equal to 0. So first we handle the partial derivative with h, and then partial derivative with h, then we have this one. Next we handle the partial derivative with s, partial derivative with s, then we have this one. And then finally, we can make it small. Finally, we set the partial derivative with lambda equals 0, which as always is just the same thing as the constraint. In practice, you can of course just write the constraint itself. But I'll write out the partial derivative here just to make things clear. So this one 0, this 0, so basically we have only this one over there. Now putting it together, now we have h and s, we have h and s, so we put the together. This is the first element, so this part, the first element gradient, second and third, so we have three equations, three unknown. In practice, you should almost always use the computer once you get to the systems of equations like this. Actually, once you reach this one, basically you can do optimization routine, right? Sum of these three, square sum of these three should be equal to 0, and then you plug that into the optim in the R in the previous class, then you can solve this one. But in this case, actually, you can solve this one with pencil and pen. In practice, you should always, almost always use a computer once you get to the system of equation like this, essentially because the equation will likely to be more complicated than this in real application. Once you do, you will find the answer like this one. So this is basically answer. This means you should employ, so because this is answer, you should employ 667 hours of labor and purchase 39 tons of steel. And using this one, we have this one. We have this product. The interpretation of this constant is that lambda is 2.593 is left to the next article. Okay, interpretation this value. Okay, we have this value. What is the interpretation of this one? We will cover this one shortly. So in this article again, here to solve the problem, to rewrite the problem, Paint. Well, to take a look at this problem again, look, our level, what we want is basically we want to maximize this one. Actually, let me just write down. And still 1/3. By the way, it is called Cobb-Douglas function. In economics, it is called Cobb-Douglas function in economics. And then subject to budget constant, money you can spend is this one. So $20 per hour, and this is cost. Plus cost of the steel is 170 S, and this should be $20,000. So again, in order to solve this one, we set up Lagrangian like this. So instead of writing, let me capture this one. Okay, let me capture this one. So this is Lagrangian. It's big. Let's make it smaller. This is Lagrangian. Instead of Lagrangian. But the thing is that I write down again this equation again because I want to introduce a simple technique, scale. Okay, shortcut to solve this problem. Because this is we have a power function. If we take log of this one, if we take log of this part, then if we take log, multiplication becomes sum. Power becomes multiplication, right? So if we take log, it is much more convenient. Moreover, log is increasing function. So maximizing this one is same to maximizing log of this one. So if we take log, this tells us that log of 200 H 2/3 and S 1/3 is log of 200 plus 2/3 of H plus 2/3 of log H plus 1/3 of log S. So it doesn't matter whether we maximize this one or this one, right? Because log. Furthermore, we can ignore this one. So our final, because it is irrelevant in our maximization problem, right? So it means if we write down Lagrange again, then we have 2/3 log of H plus 1/3 log of S. It doesn't matter whether we maximize this one or this one, right? This one. And again, we write down Lagrangian H plus 170 S minus 20,000. Okay. Now, next step is the same. So if we use log, it is much more convenient. So next step is the same. We can simply calculate gradient del of Lagrangian. So this first part, if we take derivative H, take out derivative log H is 2/3 1 over H, right? Take derivative of log H with respect to H, it is 1 over H. And then we have minus 20, right? And then second part, if we take derivative of S, it is the 1/3 and the 1 over S. Then what? We have lambda over here. We have minus 170 lambda. And finally, if we take derivative of lambda, we have 20 H plus 170 S minus 20,000. And then this one should be 0. Well, now we can easily solve the problem. So from the first, let's take a look at H. H is what? We have 2 over 3. And then if we solve H, then 1 over 20 lambda, right? H looks like this one. right? Am I right? It is right. So S is what? S is 1/3. Sorry. S is right, 1/3. And then, sorry, let me delete. S is the 1/170 lambda, right? Now we plug these two into equation, and then plug these two into our body constraint. Now you can plug these two our body constraint. So they are this one, and then we solve it, and we can plug this one. Then what we have? We can solve lambda. Once we solve lambda, then once we solve lambda, then plug lambda again to this one, then we can get h and s. So if we log, this is much easier, right? So basically, let's plug in, solve h, then 20. If we solve this one, then what we have? This is a bit messy, but now we have 20 multiplied by 2/3 and 20 lambda. Well, they beautifully cancels out. Plus 170 again. Again, they beautifully cancel out. Equal 1,000, right? So basically, so 1/lambda 2/3 plus 1/3 equals 20,000, and this is 1, right? So lambda is in this case 1/20,000, right? So h equals to 3/2, and then if you plug this one over here, then 1,000, right? So basically 2,000. And then likewise, if you plug this one s equal, well, this is the slightly more complicated, but well, 1/3 and then 17 of, yeah, something like this one. So we got the answer. So this is the answer. And then you plug this one into the 200 h 2/3 as 1/3, plug this one 10. The answer is what? The answer is, I think the answer is, what was the answer? The answer was, yes, this one. Yeah, so this is process. And here, this solve lambda, and this goes to, yeah, this one. This is the process. Okay. Now let's take a look at another equation. Now maximizing dot product. Let the three-dimensional vector be defined as follows. This is three-dimensional vector 2, 3, 1. Now consider every possible unit vector you had in three-dimensional space. Okay. Now for which one is the dot product the greatest? Oh, so we have a dot product. We learned the dot product. Dot product measure basically how much dot product measures the extent to which two vectors are in the same direction. So we can intuitively solve this one. So it is unit vector. So unit vector means that the normal, the length of vector is 1. So in this case, okay. So this is 2, 3, 1. Below is a two-dimensional, but not much change in the intuition as much. We move three-dimensional. So let's take a 2, 3. So the first 2, 3. So it is 2, 3, 2, 3. So V is somewhere, maybe it is 1. So anyway, let's say this one. So in this case, we among this unit vector is this length of this vector is 1. So basically circle. So in this circle, so out of this possible unit vector, we want to maximize dot product of this one and this one. And we know dot product is basically about how much they're in the same direction. So instantly we know the answer for this solution is we have a solution if they are in the same direction. That would have the maximum, dot product. On the other hand, this yellow, actually, let me copy this one over here. In fact, the better one is here. Well, it is the dot product. Therefore, well, dot product is about same direction. Therefore, if we have here this way, well, nothing. If we follow this direction, well, yellow is not good, too weak. Let's sky blue. Well, if this one is like this one, then we have max dot product. Okay. On the other hand, we have this one that would be mean dot product, minimum dot product, or u hat v, or minimum dot product u hat d v. We would have something like this, right? So we know the answer. And then let's check Lagrangian, whether it finds the solution very well. The solution, let u, x, y, z, and the norm, the fact that the unit vector means that its magnitude is 1, so the length of this one is root of x squared, y squared, z squared, which is equal to 1. And then, well, we can just square it, and we don't like it, so make it 1. So it is basically ball in the basically sphere in the three-dimensional space. So this is our constraint. Okay. Now maximizing u hat v, u and v inner product or dot product u v means that we want to maximize the following quantity. This one. Okay. So dot product is this one. Actually, you can solve this one better if you regard that as a cosine and sine. Actually, you can solve this one better. Okay. We have explanation over here. Not so much, but let's see. So this is Lagrangian. So let's take a look at gradient. This is x, y, z, and then the gradient is this one, and set is gradient 0. So we have this one. So it is very easy to solve if we do the 3 lambda and 0. So we have 4 equation, 4 unknown, x, y, z, and Lagrange multiplier. And by using 3, we can express x, y, z in terms of lambda, right? X, y, z. So x, y, z is 2, 3, 1. This one. This is exactly, in the previous case, 2, 3, 1 over here, 2, 3, 1 over here, right? Where v inner product. So basically, they are in the same parallel line, exactly in line with our gas. So they are basically parallel line. So if we write this one, u is x, y, z is 1 over 2 lambda, and this one basically parallel to v. Okay, therefore u hat is proportional to v. Geometrically, this means u points in the same direction as v. There are two unit vectors proportional v, either this one or this one. One which points in the same direction. This is the vector that maximizes this one, so max. One which points in the opposite direction. This one minimizes this one. We can write these two unit vectors by normalizing v. So basically we have v. So by normalizing v, right? This one max is this one, min is this one. So magnitude is root 14. So u max is this one. Minimum is simply we put minus over here, right? So basically, we are looking for vector with the same direction, and the length should be 1. So we can simply normalize this one, right? So our strategy is to find this, or blue arrow, sky blue arrow. We simply normalize V. Normalize means that normalize V. So max. Therefore, max is simply V hat divided by magnitude of V. And minimum is inverse, of course. Right? So mean is we should have opposite direction. So it is same direction. And to opposite direction. The other way. Equal now minus, right? Divided by V. So this is our answer. Prove it. Yeah. So this is max. Just keep the Lagrangian and then you can do this one. Okay. Okay, we learned the examples. And the next, how about second order condition? Well, once you solve the Lagrangian, it tells that the solution is critical point. But in the first order condition, in which del of Lagrangian is 0 or Lagrangian is 0, we don't know whether it's maximum or minimum saddle point. If we want to know maximum or minimum saddle point, we have detailed explanation in this link. You can click this one. You can reach here. This is well written, a bit slightly complicated. Basically, there is a strictly local minimum, and we have strictly local minimum. So there is technique. So again, once we solve Lagrangian like this, del equal to 0. Once we Lagrangian 0, then we want to know whether a point is minimum, maximum. Right? In this case, it is maximum, minimum. So once you set Lagrangian equals to del of Lagrange equals 0, it finds the solution 2 points in this case here and this one. And maybe you want to know which is maximum and which is minimum, then you have to check second order condition. And about second order condition, you can find the discussion here. This is condition for local minimum. This is the condition for local maximum. And the other thing are all saddle point. So first you check the first order condition like this one, and then you check second order condition discussed over here.